Hi, everyone, and thanks for coming. My name is Attila Szegedi, and for the past 2.5 years, I've been working at Oracle's Java Lang tools, and during that time, mostly working on Nashorn, which is our new JavaScript runtime. And well, there was a bunch of things to discover and learn in this journey so far, and we have a lot of additional things ahead of us. But with the things that we achieved so far, I think we did hit on some very interesting experiences and some very interesting results, and this is what I will be sharing with you today here. I hope you like bytecode. So, oh yeah, this is our I work for Oracle slide. Don't believe anything I say. Don't purchase anything based on what I told you. I might be lying. I almost certainly am. So what's Nashorn? We started out with creating a new JavaScript runtime on top of the JVM. Oracle's JDK, and before that, Sans JDK since Java 6 has been shipping with a JavaScript runtime that was a version of Mozilla Rhino, but it had its issues, so there was a decision to create a new one. Nice thing about Nashorn is that it is completely open source. All of the development that we do is in the OpenJDK repository. There's no closed parts. There's no walled off secret source, whatever. It does ship a standard part of the Oracle's Java since Java 8, so it's in there. You can just use it. I will not talk to you about how to use it. You can find this. This is not the top. This is not in scope of this talk. You can access it from command line. You can use the JavaScript javax.script APIs, or you can also directly use the JDK Nashorn API scripting package. What's interesting about it is that currently we do have no interpreter. I'm saying currently because it's not out of the question that we might want to have one in the future, mostly for faster startup reasons, but we don't have it currently. So Nashorn starts out with compiling the source code to Java bytecode and then running that. It is fully ECMAScript 5.1 compliant. As a matter of fact, I have a tweet that I couldn't find now and put it on a slide, where about 2 years ago in a bar in Stockholm, I was running the ECMAScript 262 test suite that consists of some 11,500 tests, and I have the privilege of having been the first person that had all of those tests 100% pass on his laptop. Of course, this also meant that I had 2 tests that were not passing for a month, and I was working on that damn 2 tests for a month before they passed, but it is just the way it is. Nashorn is also security-minded, although we won't be talking about that. Another reason to replace Rhino was that poor thing hails back from Java 1.1 days, and well, it is not exactly, it does have no idea about the Java security model. With Nashorn, we did make sure that all the code generation, the typical issues with privileged code execution and so on that you have in Java, we spend an amazing amount of time on actually getting this right. It's also our proving ground for invoke dynamic. Nashorn uses the invoke dynamic under the covers for its to basically have dynamic execution on a fairly static runtime, and we are probably the biggest user of the invoke dynamic right now, and we also serve as the grain of the sand in the hotspot team's oyster to try to prod them into producing a Perl. They're still not completely there, but they're getting there. So far, we released it in Java 8, and then in 8.20 we did some security fixes, and 8.40, which is our current death march, is the big performance release, and I will mostly talk to you about this. And then Java 9 will get everything that Java 8 has, and plus some. why do we have this performance focus? And this talk will mostly be about how to make a fast dynamic language runtime on the JVM, because, well, let's face it, writing a slow language runtime is fairly easy. Getting a faster one is somewhat more complicated. With a throwback to the Kolmogorov complexity and the fortunate fact that that function is actually not computable, that's also called the compiler writer's job security theorem, which basically says you can spend a lifetime writing optimizations did I say runtime? You can spend a lifetime writing optimizations in your for your system, because you can never prove that there are no optimizations left. But which means I might actually retire one day and say that all my life I was optimizing Nashorn, although that might not be the exact same story that I would like to tell to my grandkids, so we'll see. So how are we doing? The blue line that you almost cannot see is Rhino, and the line that's like normalized was JDK 8 Nashorn, and currently the green offshoots is the Nashorn 9, the JDK 9 performance, the same thing that actually goes into 8U40. We are backporting it in a lockstep. Well, things got faster. They always ask me, so how fast is it? And that's a question you can only answer with an awful lot of qualification, right? Next question is inevitably, how about V8? Well, this is the state-of-the-art versus V8. V8 is faster. It will probably always be faster. We don't want to really, we don't claim to compete with V8. As I said, we want to have a modern runtime on the JVM. We want to have many things, but we are not shooting for fastest runtime, fastest JavaScript runtime. There are some things that we cannot do that V8 can do. V8 can do things like change the object layout while it's garbage collecting, because you have this fun thing where it's an actual live code from Node.js where they allocate an object literal using curly braces, and then they start using it as an array, which is a completely legal thing in JavaScript, although you would probably better communicate your intent if you use the square brackets instead of curly braces. But the good thing about V8 is that it can realize when it's doing garbage collection, it needs to inspect the objects anyway, so it will look at it and say, hey, this thing looks a lot like an array. Why don't I just change the internal representation to be an array? Us having to map things to objects on the JVM, we obviously can do that, and there are some other things, but the good news is that number crunching performance-wise, we are really catching up. That's actually something I wouldn't have said a year ago, but we are getting there. So, what optimizations? What's the things that you do in your dynamic language today if you really wanted to go fast? So, things that we realize we need to do. We do parameter type specialized compilation, which means that if you have a function and you invoke it with int parameters and double parameters, we will actually compile two versions of the code. Yes, there is a danger of combinatorial explosion. No, in practice it doesn't really happen. And we are also very narrow with our, well, to say it this way, our numeric tower is a very small tower. We only do int, long, double, and then object. The other crazy thing that we did was we actually implemented a scheme for on-stack code replacement with, that we needed for gradual deoptimization. Again, what is this about? Well, in JavaScript, when you retrieve a property from an object or you retrieve an element from an array, you have no clue statically what its type will be. It can be anything, right? It can be an object, it can be an int. You cannot tell until you retrieved it. So what optimistic typing says is, let's be optimistic. Let's just presume everything will be an int. And then proceed happily with that assumption. Of course, when it does not work out, you need to somehow bail out of that particular code, because if you retrieved an element from an array and you thought it's an int and you try to, and the rest of your code in bytecode says I add, you try to do an integer add on him, right? You cannot have anything that's not an int on the stack. The Java verifier will not let you. in the first place. So you need to then take that version of your code, you need to bail out of it somehow, recompile a new version that says, well, I know that that array is known to return doubles, so I will now treat whatever comes back as double, and instead of iadd, I will use deadd. And then you need to keep running with that. We'll get to it. We have static code analysis, which is funny because it's a dynamic language, and there is a slew of ordinary compiler optimizations, those that you can read about in books on writing, say, a C compiler. You also take advantage of runtime context during compilation, which is one of the more inspired things that I think I did in a past. It was quite funny when I figured out we can do this, and it was even more funnier when it worked. So, parameter type specialized compilation. As I said, if you have a function in JavaScript, say you're squaring a number, and you invoke it with an int and you invoke it with a double, then what happens is that we will actually compile two versions of the code. Oh, and by the way, we are doing lazy compilation. This function square, it gets parsed. It doesn't get compiled. It's only on the first invocation with particular parameters. If we don't have that type of specialization, that's when we will actually go to the trouble and actually compile that version of the code. I can actually demonstrate this pretty easily. I will be switching between live coding a lot here. So here's the exact same code. Oops. Yep. And let's just put some markers here that will show you how things go. So if you just run this code in a pretty dumb manner, then obviously you get this result. Now, if you add some logging for recompilation, is this font large enough? I can make things larger. Do you see it? Okay, cool.
Larger, please.
Larger? Okay. Yeah, maybe. We need to balance between size and actually seeing something. Okay, is this better? Okay, so as you can see, the program starts running and, oh, actually, crazily enough, even the program is lazy. It shouldn't be, but it's just, we didn't want to special case it. So it prints this first line, and then it actually says, hey, I need a type specialization of the square function that will take an int and return an int. How does it know it will be returning an int? Well, it doesn't. That's the fun part, is that's also something that, based on your input parameters, you might have an optimistic guess at what the return type might be, and that can actually also evolve over time. It's just the initial guess. It knows that it will be receiving an int, but that it will be returning an int is actually a guess. So, as you can see, it compiled the int version here, printed its result, and then it compiled the double version here. And as you can see, it actually says, okay, I'm compiling a double, I want to get back an int, but then a weird thing will happen here. You see this rewrite exception. That's actually telling it, I am trying to return an int from this function, but what I got back instead is a double. So at this point, it needs to regenerate the code so that it returns a double, and then return that. If we dig deeper, nice thing about Nashorn is that if you want to play with this, you can just do whatever I did. PC is shorthand for print code. You can see what it does. So we have the int version, which, loads the argument, does a multiplication, which is not an ordinary multiplication, mind you. It's a dynamically linked something and returns the result. And then you also have the double version, which, as you can see, will be returning a double. So, and of course, if I did a version that took an object as its argument, then the compiled version would be this naive JavaScript, which just takes its argument, does the JavaScript conversion to a number, and does it twice and multiplies and returns the result. The reason it has to do it twice, sorry, I'm just going through my slides. The reason it has to do it twice is because JavaScript objects can customize their number representation, and it can be stateful, so you cannot just retrieve it once and use it twice. That's another benefit of being able to use primitives, is that you know that they cannot have any of this fancy business going under the covers, right? An int will always have the same value, no matter what. And objects being mutable, oh well. What's funny is that, and that's just actually a new slide that I inserted based on a conversation yesterday, is that this thing works with higher order functions too, as JS function under the hood is actually a holder of all of its type specializations, and we propagate the types from the top. So if you take the simplest possible higher order function that basically says apply this to an argument, apply this function to an argument, and you invoke it, then what this will do is it will generate two specializations of apply, one that takes an object and an int, and another that takes an object and a double, and I need to really reverse the order of the arguments there on the slide. It will be invoking f, and one version will be invoking f with an int, and the other will be invoking f with a double, so they will actually end up invoking square with an int and square with a double. So it just works out really nicely. It's, as I said, I need to, actually in my example code, I have this right. I have it here. This is the exact same code. So if we compile this thing, we will see that we have a version of apply that takes an int, returns an int, and takes an object. That's the function, right? And it will just load its object argument and do a dynamic call on it. And it will say, I will pass it an int and expect an int to be returned. And when this executes, that's when we will first compile the square version with an int. And then we also will have a version that takes a double and hopes that it can return an int. It does not know what's the type of it doesn't know what will the square function return if you pass it a double. It hopes back for an int, but it can fail, and it will actually fail. So you will see that we will have yet another version of apply compiled after a while that at this point it says, if I pass a double to this function, it will be returning a double. So it just gradually discovers the types as it goes. All right. So we also do deoptimization on arithmetic overflow, because in JavaScript we are not allowed to overflow. JavaScript specification-wise has no idea it has no idea whatsoever about ints. It's completely defined in terms of doubles. So using ints is an optimization that we do. So if you take our square function and you actually pass it something that when multiplied will overflow the int, then the square function itself will have to deoptimize. And yeah. Well, do I have this? Yes, I do. So first we have takes an int, returns an int. And then after it failed with this input, it will become more conservative. It will say, well, you know, the square function, if invoked with an int, might actually return a long. So it will load its arguments, widen them to longs, and then perform a long multiplication and return that. All right, so the invoke dynamic that we link to for the multiplication actually is something that invokes java-lang math, multiply exact. These are new methods in java-lang math that throw arithmetic exception and overflows, and that point we catch those, we we perform the multiplication as longs in the newly constructed exception. As you can see, we do a long x times long y there, and we throw back a new exception which also contains an identifier of the location in the code where this thing happened. We must perform the operation, return the result, because, well, all of this must be transparent with regard to the execution of the program, right? That we are internally throwing exceptions, regenerating code. From the point of the external user who runs the code, this must not be observable. We have similar deoptimizing compilation for property types. If, for types of properties. If you're retrieving a property foo from A, for instance here, we'll again have an assumption that it's an int, and we generate a dynamic invoker which invokes the function, invokes the property, and the return value, it tries to treat it as an int, and if it's not, it will throw an exception to regenerate the code. So sometimes if it gets really widened, then if this a foo is actually a double, then we will end up generating a really nice version of the code that says, okay, if it's a double, then I will just use double multiplication here. And this is an example of static type analysis working hand in hand with optimistic typing to make sure that the code is as nice as possible, because double multiplication cannot overflow within the JavaScript semantic, right? It can become infinite though. All right, so how do we do this? How do we deoptimize running code? Because normally the usual way to do this is you need to recompile a new version of on the fly, but what's more complicated is that you need to replace your running code on top of the stack. Now, runtimes that do this are obviously solving this problem. Our issue was that we try to solve it in a way where we don't do any magic tricks. We want to do it in completely Java specification compliant way, not using any VM tricks. So we did achieve this with a pure bytecode solution, so it runs on any JVM, not just Oracle's JVM. As I said, Nashorn is in OpenJDK, so any OpenJDK licensee can take it and use it on their system. It does not have to be it does not have to be Oracle's hotspot. So what we did, you saw it that we throw an exception where type assumptions are too narrow. And whenever function that can be deoptimized is linked, we use the invoke dynamics try-catch combinator to catch this exception in the caller. It must be in the caller because we need to jump out of the function that needs to be deoptimized. We need to remove it from the stack. So we need to jump back to the caller. The caller catches the exception, derails into the compiler. It generates two versions of the code. The new version of the code with a wider type at that point, it installs it wherever it needs to be installed for later discovery if some other site also invokes the same function. But we also need to compile a separate one-shot continuation version of that code as well. And then we need to invoke that guy to resume execution as if nothing happened. This looks like this. This is a typical example of a rest of method in the previous example for a foo times 2 is we take asm, and in order to not make our life difficult, we just generate the same code as for the normal version of the function. We don't do anything fancy. We just basically feed asm with the same instruction visitor sequence. Except at the very top, we put a goto to a very late label. And that very late label on the bottom is something that takes this rewrite exception, which contains the full encapsulation of the state that we captured at the point of the failure where we need to recompile. It restores the local variables, and then it restores the state of the stack from those local variables, applies any type conversions that might need, which might be tricky because maybe you were initializing an array of ints and one of your expressions became a double and you actually need to have an array of doubles right now, at which point you might have a value on the stack that we just transparently and nonchalantly just replace from an array of ints to an array of doubles now. And after all that was said and done, like a cherry on the top, you put the return value, which is now a double, and then you jump back to whatever is the rest of your execution. So that's how the rest of method works. I'll show you an example. Hey. Okay. All right. Oh man, the computer is behaving. Okay, I cannot believe this. Look like the presentation gods are not with us, and this otherwise trusty MacBook Pro just decided to, I don't know, look up. Maybe it's just a display problem. Let me see. Well, it's still. Okay, I can still go through my slides, so maybe that will be sufficient. So, extremely simple terms, what it does is that we have this try-catch combinator where you say, okay, let's invoke the function, and if we get the rewrite exception, this is all put in a dynamic in the call site, in the caller. Then, if you get the exception, then you do the thing, which to do the thing is recompile the function, store the new version store it with the immutable function data for later invocations. You need to invalidate all the already linked call sites that were linking to the potentially old version of the code, including this call site. And then you need to generate the continuation version, and you need to jump into it. However, there's some tricky stuff, like you want to recompile what if you need to recompile a recursive function? A mutually recursive function that can have another copy of it, an arbitrary number of stack frames further down. We don't want to exhaust the stack on cascading recompiles, because if you deoptimize something and you're running the rest of method, it itself can hit another point where it itself will deoptimize and so on. For that, what we do is that instead of invoking the continuation, we return the method handle that's the continuation, and we fold it into a method handle exact invoker. I don't expect that you necessarily understand all of that. I'm just trying to illustrate the amount of stuff that we needed to take care of. And then we go and bother the VM hotspot, the VM team and the team that works on method handles. We come to them, it's like, hey guys, there's this catch combinator. It performs really poorly. And they're like, yeah, whoever uses that. Oh, well, we use it everywhere. Oh, you do? Yes. And we need it to be fast. Well, it has a fast path up to 8 arguments. That's not good enough. We have some benchmarks, and this is JavaScript, where people routinely pass, I don't know, 15, 16 arguments in the functions. Yeah, it's ugly, but who can prevent them, right? So we need the fast pass for the catch combinator to be fast, no matter how many arguments and what their types are. And then they go away and grumble and come back a few months later and say, here. Of course, getting right all of this, it really scrapes at your sanity at the time. This is my tweet from a few weeks ago when I was working on Nashorn's parser so that it can skip. We do a lot of recompilation, so it's nice to skip already in the parser things that you don't need, like nested functions. And I have this great board game, Cthulhu Gloom, that I like to play with my wife and kids. And I said I can start illustrating my work with cards from it, where you like inflict. The card game is about inflicting misery on members of a family that are put in your care. And this is one of those, like, delve too deep, minus 20 points. And on the right-hand side, you have also this like little icon for special insanity modifiers. And this is my colleague Marcus in deep thinking about some JavaScript object shape problems. So, come work for us. Nashorn has an extremely simple type hierarchy, int, long, double, and object, and we just any of those can be widened, and it's monotonic, so we can never end up with a circular thing. while deoptimizing. The optimization, when you really think about it, is really just a stepping in a lattice of type tuples, because every point in your function that can deoptimize has a current type, right? So if you have like 4 points, you all start with like int, 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 int. Everything is an int. I'm so happy, I'm so optimistic. Everything will be an int, everything will be great. And then you deoptimize and say, well, maybe the first argument was a J's for long, was a long, but everything else will still be an int. And then maybe something else deoptimized. So what happens is that you have an input to your function and you try to run it, and sometimes you have your data flow pipeline, which is at first is int wide, and then whenever something gets stuck in it, you widen it a little bit and carry on, and eventually you hit a point in the lattice that works for all the data that you have thrown so far on into your function. Well, maybe some million iterations later something will come again that will widen it, but hey, the machinery is still there, you will do it then. But usually things stabilize, and then you have the super pessimistic bottom of the lattice on the right, which is everything is an object. Sorry. Sometimes you don't need to be optimistic. Like if you are doing a multiplication of 2 numbers, but you know that you feed it into something that truncates the value to sine 32-bit int, then we don't bother. Again, a nice place, a nice reason for using static type analysis is that if you have this pattern, it's using asm.js to force the arguments to be ints. We just do an IMAL here and don't carry and don't worry about the overflows because they're chopped off by the OR 0 anyway. Oh, and then there's this thing where, okay, so are we in compile time? We are recompiling code, but are we in compile time? Well, we're not. JavaScript does not define compile time and runtime. It just says, here's the source code, execute it, right? Anything that's in between, specification doesn't care. And what we can do here is that one of the realizations was that, hey, it's a dynamic language. You jump into a compiler, but you're actually running. You have the values of all the variables and objects in the lexical scope, and you can use them. Yay. So what we do is that we can actually skip several of these steps in the compile, in the type lattice. For instance, if I invoke a function that takes an object and I retrieve 2 properties from it, o.x and o.y, at first I will start with the assumption that x is int, y is int, and their multiplication will be an int. So I have my type lattice has these 3 ints as starting point. And then I invoke it with this object literal where both x and y are doubles. So when I retrieve o.x, I will fail to retrieve it as an int. I need to recompile the function, so I derail the execution into the compiler. But what I do now is that naively, I would just say, well, okay, o.x is a double now, but o.y might still be an int. I will be optimistic about it. And then I start running the new version, and that o.y also fails being an int, and then I need to recompile again. Okay, oh, damn it, okay, o.y is also double. Let's recompile again with this in mind and carry on. So that's 2 recompilations. But we cut that down to 1 because when we recompile o.x, we actually tell the compiler to try to evaluate side effect-free expressions. So if o is just an ordinary local variable and the y is a property with no getter, so it doesn't have any side effects, you know it's just a field getter, it will actually peek into it. And if it says, well, that's a double as well, I would just emit the code to be a double. So we curb the enthusiasm, so to speak, of the compiler, if we know. And it really pays off when you have things like this. This is actually the Octane Box 2D benchmark that does things like this. Now imagine if these are all doubles, and we would always just presume that one of these is a double and the rest can still be ints, and you would recompile the function, evaluate the next expression. Oh, damn it, I need to recompile again and go back and just, it would crunch through it, but it would be slow. It would be horrible for warm-up time. And with this, basically, whenever it hits recompilation, it will try to peek at the values of other available variables and just try to evaluate them and preemptively deoptimize, basically. So static type inference in a dynamic language runtime is also sort of an oxymoron, right? Except it isn't, because at the end of the day, we are targeting a static language runtime. Well, static virtual machine, sorry. JVM is statically typed. It has separate operands for arithmetic on ints, on arithmetic on longs, on arithmetic on doubles, and so on. So what we do is we do actually calculate types of expressions and local variables, and we do a bunch of we do the propagation, as you could imagine. It's standard compiler stuff. It's not terribly exciting, except for the fact that we did it and we saw extreme benefits. After I spent probably 3 months from January to March this year writing the static type inferencer for it works within a single function for Nashorn, and the number crunching performance, number crunching numbers, they went through the roof really. Crypto benchmark, other benchmarks that are heavy on calculations like Box2D as well, they just got amazingly faster. And what's super frustrating is that I have a bunch of example code that I was going to live demo to you right now, but I cannot comment tab out of my presentation. So I guess we're stuck with me speaking and you believing what I say, although I had the slide saying that I'm lying. So. So there's we need to handle a bunch of tricky control flow situations that you don't really think about a lot, like control flow into catch blocks, right? Okay, so it's like, okay, how boring is this? But it has to be done. It's the problem with Java, the blessing really with the Java bytecode is that it needs to be statically verifiable. So it means that you need to be able to have a definite type for a local variable at any time. So what we do is that if you can enter the catch block or just fall out from a try catch in such a manner that the value of A might be a double, then you must ensure that no matter how the execution reaches the catch block, it has to be a double. Now, we started with an int, we define it as an int, but when you enter the try block, we just insert like a synthetic widening into a double. But on the other hand, that's so wasteful, because if it doesn't go into the catch block, now I treat it as a double, whereas I could treat it as an int. So what we do here is that we keep 2 live values for the variable. So the way our storage for local variables is constructed is that the variable I will actually have assigned 2 bytecode slots, one for its int value and one for its double value while it's executing in a try block. And whenever it has a live int value, it will be used. So if you print the A there, it will actually, in the first line, it will actually use the int value, and you assign it another int value. What happens here is that we store the int value into the int slot, we store the widened double value into the double slot, and still both of them are live. And then when the A equals 2.1 comes around, we say, well, it's now defined as double, and the int value is now dead. And then but this all ensures that when you enter the catch block, the int value is dead there anyway, but you will always have a live double value, even if you somehow went to the catch block because one of the prints threw an exception, which it won't do ever, but just for illustrating purposes. So these are things that need to be solved because of Java static verification of types, and because we didn't want to just stupidly widen the value into int for the sake of the catch block if it's not necessarily true. It works for other things as well, not just catch blocks, right? You can have an if block where if true something, and then you have a long if block that's manipulating variables, but they are never used outside or used differently outside. So we try to keep the value as narrow as possible. So here's another example. In the if block, if you assign I equals 1, then the y will actually use the int value, and then we exit the x block, then you need to widen it. And so this is real classical control flow join points type coordination. But again, it's not specifically interesting because of the fact that we do it. It's not specifically interesting because it is what it is. It's all the type theory stuff. It's interesting to see that we did this in our JVM-based dynamic language, and we did reap quite big performance benefits from doing it, which again might not be terribly surprising, but at least now we know that it works. We do a bunch of death code elimination as well. We did have to use something that's called type liveness. I spent maybe a week, like in a shower during the runs, trying to figure out a liveness analysis algorithm on AST. Turns out you can't. Or maybe you can, but it would be horrible. That's because a liveness analysis always goes backwards in the control flow. And ASTs are not really well geared for that. So it's not a luxury really, because JavaScript has this brain dead thing where if you declare a variable within a block, it's live outside of the block as well. So in this case, it's fine. X can remain being an int because it's not used outside. But if you do this, you actually use it outside. It actually needs to cope with the fact that, okay, so let's imagine that we didn't say I less than 10, but I less than something that I don't know what it is. Maybe we didn't even enter the loop body, so X needs to be widened to object. But when do you widen it? Again, the static type proving for the Java verifier makes it really hard to eliminate like widening of X to object on every back edge of the loop, which would be horrible if you had to do it. But we don't have to, so that's why it's not a luxury to do. I don't have time to talk about a lot of things. As a matter of fact, I think I'm completely out of time. But if you want to stick for another 3 minutes, I can just tell you real quick what is it that we want to go towards with this. Right now, this is Nashorn's compiler pipeline. The code gen at the right is like a more bold arrow, and it is where the heavy lifting right now happens. Code for optimistic operations, continuation handling, self-assignment stores, whatever. We do all of that there. But I'm not happy about it. What I want to do is I want to move it in a previous phase of the compiler pipeline. It doesn't exist yet, that I call the dynamic code gen. That would be creating something like a dynamically typed bytecode, which would look something like this. So if you have a function square, you could emit something like load x, load y, multiple return. And it would be our library that would convert that into what you have on the right side, figure out whether there is any optimism that needs to be done, and emit the final bytecode. So the benefits of this are reuse, right? V8 has almost 1 million lines of code. Nashorn has 270,000 right now. And the reason for that is that we use a lot of everything in the JVM. Now imagine if we can extract a lot of things we have in Nashorn and give it to you as a reusable library for building dynamic languages. That's what I want to do. My elevator pitch for what I want to do in the future with this project is like LLVM, only for dynamic languages on the JVM. Basically give you this almost bytecode, except you can use symbolic identifiers and you don't really care about types, and it will run your static type inference, prove as much types as it can, and deal with the optimistic recompilation for all the types that it cannot prove statically. That's my ultimate goal for this. And these are various examples. Oh, lexical scope getters, right? Almost every dynamic language has lexical scoping. JVM doesn't have it. That's also something that we can just fix for you. So in your thing, you can just be getting. You can just say like load X, and you don't have to worry where the X is defined in your lexical scope. We can just make sure that if it's outside of your current local scope, then instead of a local load from bytecode slot, we can do an optimistic getter from your scope, and so on and so on. So that's the thing. Summary is some things are really hard to do here. Static analysis, the whole thing we did, type specialized on-stack replacement. I didn't even talk to you about our array representation, optimization of built-in, like array push-pop, string caret, and things like that. This whole optimistic on-stack replacement solution. And we have solved a bunch of these problems with Nashorn and would like to offer them eventually as a reusable library. And what we also need for that is a suitable code representation. As it turns out, AST is too high level, JVM bytecode is too statically typed. We need something in between that hits the sweet spot, which would be this, in my imagination, something that is very similar to bytecode, except that you don't have to worry about these bunch of things that I just explained to you. All right, that's all I had. Apologies for overshooting, and thanks for listening.